Hey everyone, and welcome back to PrepFusion. I'm Anish, and today we're going to solve a very interesting question from state space analysis, right? Basically, from the topic of controllability and observability. Generally, this is the hot topic of Gate, right? Generally, one question at least comes from the controllability and observability. So here we have been given a question. This is a Gate 2021 EC question, right? So the question is given like this: that we have a electrical system shown in the figure which converts the input source current is to output voltage VO. Okay, and we have to tell that the current IL is the inductor current, VC is the voltage across the capacitor. Okay, and the both are assumed to be taken as state variables. Okay, both are assumed to be taken as state variable, and both of them has initial condition to be 0, right? That is given this. Now you have to tell that whether the system is completely state controllable or completely observable, or it is it is not observable, controllable. What is it, right? What is the system, right? So by just observing the circuit, can you tell something? So generally what you will do, you will follow the general method, right? First you will write the state space representation, and from there you will find the system matrix A, right? And the output matrix, then the that input matrix, all those things you will find, right? Then you will find QC and QO, right? And if the determinant is equals to 0, then we know it is not controllable. And if QC determinant is equals to 0, then we know it is not controllable. And if QO determinant is equals to 0, then we know it is not observable, right? So yeah, that is the general method, and that is not correct. That is correct. That there is nothing wrong with that. But we can solve it in other ways also, which will give us the answer solution faster. So first thing what I can notice here is, like, if you notice carefully, right, this is the output. My output is taken here. Now can you tell me what is the order of the circuit? So I hope you have studied transient response by now. Can you tell me what is the order of the circuit? The order of the circuit is what? 1. Why? Because if this current is entering here, let's say 1 amps current is entering here, so how much current should get out of from here, right? It should be what? 1 amps itself, right? Because the distribution I don't care, right? But when it gets here, right, when the two currents meet here at the outgoing, at this node, the outgoing current should be same as this incoming current, right? Throughout a network, this, let's say this is a network, and whatever is the incoming current, the outgoing current should be same. So if this is 1 amps, then this is also 1 amps, right? So if this is 1 amps, now is like the current, like, is this even changing anything? This inductor isn't even doing anything to this current, right? So this is always IS current itself. So this is not affecting the response of my system. So this is this isn't doing anything. So what is happening? The order of circuit is 1, but here the question has given us that we have taken two variables as my state variables, right? So what is the issue? If my order of the circuit is 1 only, and I'm representing using two state variables, then I'm obviously taking up extra state variables. Then what happens? Then the state space representation either becomes uncontrollable or unobservable, or both. Okay, that is the point 1. That is the point 1, that it can become uncontrollable, unobservable, or both. Okay, but I'm for sure at least one of them will occur. Either it will become uncontrollable or unobservable. One of them will surely occur. Okay, but will both of them occur? I can't say from right now. Okay, I can't say right now. Okay, I have to further check. Okay, so this is the first observation. So like this also you can solve the question. If some suitable options come out, right, you can eliminate options from here, right? So yeah, that is one thing. Now let's solve this question. Now obviously we have to write the state space representation of this one. Okay, so how to write the state space representation? So basically I will copy the circuit, right? I will copy the circuit. I will copy this here. Okay, now you will see how to write the state space representation also in a very fast manner. So whenever, like, you have to write this state space representation for inductor, right, obviously you write it in terms of IL itself. Because why? Because IL is in the differentiation format, because VL equals to DIL by dt. So VL equals to DIL by dt, hence it is in the differentiation format. That's why IL is chosen as the state variable, right? Okay, as it decides the change in the behavior of the inductor, it decides the change in the state, right? That's why IL, right? So now how to write the state space representation for this inductor? What I can observe is, let's say, like, this is my VL voltage, right, across this inductor. So if this voltage is VL across this inductor, okay, let me take another VL across the inductor, right? Okay, not like this. yeah, VL across the inductor. Okay, now what can I say about the current through this? If like this VL is across this inductor and this resistor also, right? So what can I say about the current here, right? What is the current? Current is basically voltage by resistor, so it is VL by 1, which is VL amps. So don't get confused by voltage, right? So this is VL amps itself, right? This is VL itself. Okay, current is VL. And what is the current flowing through here? Current flowing through here is IL itself, right? IL itself. And what is the current flowing through here? It is IS itself. So I can simply write a KCL at this node. Let's name this node as A, right? If I name this node as A, then I can write KCL at A. IS equals to, I'm not writing like bracket T, right? It is understood that they are functions of time. All of them are functions of time. I'm not writing bracket T. Okay, so IS equals to this IL, inductor current, plus VL, right? Plus VL. That is one thing. Now what is VL equals to? VL equals to L dit by dt. So like this is the property of inductor, right? VL equals to L dIL t by dt. How we can write this dIL by dt? L IL dot, right? L IL dot I can write, right? This is the notation that we follow in state space representation, right? So this is looking like VC. This is actually VL. Okay, you like whenever you want to write the state space representation for inductor current, right? You try to find the voltage, right? You have to find the voltage, because voltage will give you the this dIL by dt. Very important, right? So now I can rewrite this equation. IS equals to IL plus L dIL by dt. So L is 1 here, right? L is 1. So simply I can write IL dot, right? IL dot I can write. Okay. Now I can take the IL on the left hand side. So my equation will be something like this: IL minus IL plus IL. So this is my first equation basically. This is my first equation. Okay, so this is my first equation. Now what is my second equation? So now let's go for the capacitor, right? Let's go for the output part. So I'll again copy this one. So if I copy this one, right, now what I will do, so now what I can see is like I have to write this in terms of input, right? Not in terms of output. Output will come later, but first I have to write this in terms of input. Why? Because the state space representation, I hope you know, I will not explain further, because first what happens, like my x dot equals to ax plus bu, right? We use the input, right? Then my y equals to this c x, right, plus du. Okay, so that's why I'm getting the first equation right now. Okay, so solving for the first equation. So now what I can write here, this like IS is coming over here, right? IS is coming over here, and this is dividing into both of this current. This is VC, right? So this is also VC, and what is this current? This is VC by 1. So VC by 1 is VC itself. So this will be VC, right? This current is VC. Okay, I will just write this in different thickness. This current is VC. So if this current is VC, right? This current is VC. What is this current? This is the capacitor current, right? And that is like that is what we have to write, right? That is what we have to find. Because why? Because IC equal to C dVC by dt. That is why IC is very important for us. So this is IC, right? And this is what IS, as I explained before also. This is IS, right? Because whatever current is incoming here, the same current will come out here, right? So again, write my KCL at node B this time. Let's write this. Okay, sorry, this is node B, right? So KCL at node B, KCL at node B, basically IS equals to IC plus VC by 1, which is like VC itself, right? Now what is IC equals to? Now I can write my IC equals to C dVC by dt, right? C dVC by dt, where C is 1 farad, right? C is 1 farad, and I can write dVC by dt as VC dot, right? VC dot. Okay, so now I can replace this IC here, right? And again I will get the similar type of equation basically. So if I replace this vc dot plus vc equals to is. I will take vc on the right hand side, so vc dot equals to minus vc plus is, right? It is understood that they are functions of time, so I'm not writing bracket t, right? Not writing that. So now let's write the output equation. These were the input equations. Let's write the output equation. So from here itself I can say directly that my vo equals to vc itself, right? vo equals to vc, right? If I'm taking the voltage from this point, vo equals to vc, so I don't need to further go into much depth, right? So output equation vo equals to vc basically, right? So vo equals to vc, so very easy. Now can we write the state space representation, right? The matrix format, that is. From there we will obviously understand the controllability and observability, right? So let's write the standard format, right? So it will be vc dot ic dot, right? Okay, what have they given us the format like? So it is okay, il, they have, like, you can either write vc dot first or il dot first. So I will write il dot first, as I have solve for it fast, so it doesn't matter, right? It doesn't matter. Your final answer for controllability and observability will come out to be same. So this is il dot and this is vc dot, right? This is vc dot. So what does this become? This becomes basically like, now you have to understand the coefficient, right? The coefficient of il is -1 and this is 1. So I will first write it, then I will explain it to you. This is -1, this is 0, this is 0, this is -1, this is il, this is vc. Okay, plus now this, right, this is equals to 1 comma 1. Okay, and this is multiplied by is, right? And what is the output equation? So this is basically vo, which is equals to 0 comma 1 vc, right? vc, okay, this is also in matrix format basically. This is il vc. il vc, right? So yeah, this is basically this. Now I will explain to you, like, if you have studied state space equation, you will understand, right? So basically the coefficient of this is -1, hence -1 comes out to be here, and I don't have any vc term present in this here, right, in this equation for il dot. So basically il dot is equals to -1 times il into 0 times vc. So I will not explain this further because this is a question session, so this is all covered in theory. Okay, so everything is covered in theory. And this output, right, this output only contains vc, right? It doesn't contain il, so that's why 0 times il plus 1 times vc, simple matrix multiplication, right? So yeah, now let's talk about the controllability. So from this step, right, what you can do is basically you can simply find the qc and qo and check for the controllability and observability. But I will tell you one other method. What is the other method? Other method is the Gilbert's test, right? So I have taught this in my obviously theory class, right, in the control system playlist, but I will just give you a brief when I have repeated eigenvalues. Now you might ask, sir, what is eigenvalues? Eigenvalues are this, right? The I hope you have studied matrix, right? Eigenvalues of the system matrix, right? That is what do I mean by eigenvalues basically. So if you have studied matrix, then you will be able to understand this, else it is difficult, and it is difficult for me to give you the whole concept, right? So if you understand eigenvalues, well and good, else you skip to the next part, method 2, right? So using the Gilbert's test, right, if we have repeated eigenvalues here, right, we can see this is a diagonal matrix, and for diagonal matrix the diagonal elements itself are the eigenvalues, and what I can observe is here, right, my eigenvalues are repeated. This is also -1, this is also -1. So Gilbert's test has two rules. One is for non-repeated eigenvalues and one is for repeated eigenvalues, right? So obviously we'll study the repeated eigenvalues part. So here I can see that for my state space representation to be controllable, there should not be more than one Jordan block for repeated eigenvalues in a matrix, okay, in the system matrix basically. Okay, now you might say, sir, what is Jordan block? I will explain it to you, right? I will explain it to you. I have taken few examples. I will explain it to you what is Jordan block, right? And then what is the condition 2? Condition 2 is obviously it has to satisfy both of these conditions, right? Like even if it doesn't satisfy one of the condition, then we don't even have to check the second condition. We can just ignore, because if first condition isn't satisfied, then this is not controllable, that is for sure. Okay, then elements of B matrix. What is the B matrix? That's the input matrix, right? Corresponding to last row of Jordan block in E matrix should be non-zero. Okay, we'll see if you don't understand, we'll see. Now rules for repeated eigenvalues for state space representation to be observable. That was for controllable, now it is for observable, right? Now again this rule is same for same or repeated eigenvalues. There should be not be more than one Jordan block. Okay, there should not be more than one Jordan block. Now what is the second rule? The first column corresponding to each Jordan block of C matrix should be non-zero. Okay, the first column corresponding to each column corresponding to each Jordan block, right, of C matrix should be non-zero. Okay, so yeah, if you don't understand, let's first understand what is a Jordan block basically. Okay, let's first understand what is a Jordan block basically, right? This is Jordan block, right? Okay, I will try to explain it with questions, then we will understand. So here, right, I have a questions and you have to find the number of Jordan blocks here, right? So how to observe the number of Jordan blocks? What I can observe in this one, I will tell you in brief, right, because I have covered this in full course and we don't have enough time for this, right? So let's say these are my repeated eigenvalues, right? These are my repeated eigenvalues, and I will go until that when I have a one above the last repeated eigenvalue. So here, right, I'm going here. Okay, I'm going until this 5. I'm observing that I have a 1 here, so this whole thing is a Jordan block, so it is okay. So this whole thing is a Jordan block, right? I will explain with a few more examples, then you will understand. Then, right, I'm going in this diagonal element. I am seeing this is 2 and this is only alone. Okay, there isn't any repeated 2 here, so this is also another Jordan block. Okay, this is also another Jordan block, right? Simply Jordan block. This is Jordan block. Okay, and 3 is also alone. This is also Jordan block. Now here, right, here, how many Jordan blocks I have? So I will go along with this and I will find if I have a 1 above. So I don't have a 1 above this 4. They are repeated, but I don't have a 1 above this 4, right? So these two, right, these two are 2 Jordan blocks. Okay, these two are two Jordan blocks. So what will happen if I have 2 Jordan blocks, what I told, right? And if this is a system matrix A, then obviously from here itself I can say that my system isn't controllable. Also I can say my system isn't observable, right? In one shot I can tell. Okay, because I have 2 Jordan blocks for same eigenvalue, for repeated eigenvalues, right? Why I have 2 Jordan blocks? Because I don't have a 1 above this, right? I don't have a 1 above present above this. That's why. We'll do few more examples, you'll understand. Here, tell me how many Jordan blocks does it have, right? You can say 2, right? Let's see if you are correct. So I will go until I have 1, right? Until I have 1. So this has 1, fine. This is included in the Jordan block. This has 1 above. This is included in the Jordan block. Okay, then this whole thing is a Jordan block, right? This whole thing is a Jordan block. Okay, so what do you observe here? So I will go on this diagonal direction until I have a 1 above, right? Until I have a 1 above. So here if I go, I have a 1 above, so I will continue. Okay, then the eigenvalue changes, so I will stop. Okay, I will stop. Then this is a Jordan block. Okay, and this is like, these are different. Then this is a Jordan block in itself, and this is also a Jordan block in itself. Again, right, I will try to go here, but what do I observe? I can't go here. Why? Because I don't have a 1 above, so I'm not allowed. So this becomes a separate Jordan block, and this also becomes a separate Jordan block, right? But for the same eigenvalue, repeated eigenvalues, because they are 4. Now I am starting from here, I'm going down here and I see 1 above, so it's okay, it is included in this Jordan block. Then again I'm going along the diagonal direction, again I see a 1 above, so it is included in this Jordan block. So again I go in the diagonal direction and I see 2, right? And this is 3, so these have changed. So I will stop here and I will say that this is a Jordan block and this is also another Jordan block. Okay, now can we say from here, is this following the condition 1 or not? This is following the condition 1, because what does the condition 1 say? For the same eigenvalue there should not be more than one Jordan block. So for the same eigenvalue I have 3 repeating 3 times, but how many Jordan blocks do I have for that particular eigenvalue itself? For the repeating eigenvalue only 1, right? Then it is fine, right? Then it is satisfying the condition 1. Okay, that is what I mean. Now you tell me how many Jordan blocks does it have? You said 1. If you said 1, then you are wrong, right? Why? Because you continue from this path. Yes, this is 1, that is fine. Okay, then again you continue through this path. Okay, in diagonal direction you see 0 here. No, this is wrong, right? So we can't have 0 here, so we'll stop here, and this will become our first Jordan block again, right? I'll start my new Jordan block here, and I will go along this diagonal, and again I will see 1 above, right? So this also becomes another Jordan block, right? So I have 2 Jordan blocks for the same eigenvalues. Okay, for the same eigenvalue, which is 5 here, right? So again, right, this is not controllable, and this is not observable, right? So from directly by seeing the system matrix, I can directly say that whether my system will be observable or controllable. Okay, so yeah, that is one thing. And like, this is just a method, right? This is just a method to understand the Jordan block. I'm not going to the theory. I'm not going to the theory. Okay, so again, right, you go into here, right? You go into here. What do you observe? Tell me how many Jordan blocks we have. Again, right, we have what? 2 Jordan blocks, because this is 1 Jordan block, right? So I'm going in this direction, and I'm seeing 1 above, so I will continue. This is 1 Jordan block, and again this is also a different Jordan block, right? Okay, but what is different from this and this? The difference is, here I had 5 as eigenvalue present, and here I have 3 as eigenvalue present, right? So this will be obviously controllable, right? This will be controllable. Why? Because basically, right, for the repeated eigenvalue, for that repeated eigenvalue, I should have 1 Jordan block, right? For that repeated eigenvalue, I should have 1 Jordan value, 1 Jordan block. So my eigenvalue is 5, and for that, how many Jordan blocks I have? For 5 eigenvalue, how many Jordan blocks I have? I have 1. For 3 eigenvalue, how many Jordan blocks do I have? I have 1, right? So yeah, I have only 1 for the repeated eigenvalues, right? 1 Jordan block for the repeated eigenvalues. Then what can I say? I can say that at least it is satisfying the first condition. Now we have to go to the second condition, right? We have to go to the second condition. Now I will not explain the second condition here, because the first condition itself isn't satisfying. So I can directly say that this isn't state controllable and state observable, right? Directly say. So you might ask, sir, we are past almost 20 minutes and you are solving this question. So we are past 20 minutes because I have to explain it to you. I have to explain the theory, all these things, right? That's why we are past. How much time will it take you? Okay, what you will do, you will directly write this equation, right? I have to write this in very good format, but you will directly write this equation very quickly, right? And you get to this equation, then like output equation is just nothing, right? It's just 1 second. You can directly see it, and you write the matrix format, and you don't even have to write this. When you write this, right, you find a matrix and you see how many Jordan blocks do I have. Okay, I am going along the diagonal direction. I don't see a 1 above, and what do I see? I have repeated eigenvalues. If I have repeated eigenvalues, what does that mean? I have repeated eigenvalues, and for that same repeated eigenvalue, I have 2 Jordan blocks. If I have 2 Jordan blocks for the same repeated eigenvalues, this first condition for the Gilbert's test isn't satisfying for both observability and controllability. Then I can directly say from here, my system won't be controllable and observable. Okay, this will take you at max 1.5 minutes, right? 1.5 minutes. At minimum, it can take you 1 minute also. Okay, if you know everything, right? So yeah, directly from Gilbert's test. Okay, I'll copy this, right? I'll just copy this. If you don't know the concept of eigenvalues, then it is difficult. Obviously, I can't explain everything right now, right? So A is this, and what I can see is I have 2 Jordan blocks, right? Eigenvalue. Okay, 2 Jordan blocks for same eigenvalue. So hence I can directly say doesn't follow rule 1. Rule 1 of Gilbert's test. Now just do note that this is only valid for diagonal matrix, right? Okay, so we'll write here like this, right? Like obviously you have to find the eigenvalues, and directly you can find the eigenvalues only through diagonal matrix. Okay, that is one thing to note here, right? So like use this Gilbert's test when you have diagonal matrix. I have explained this in my theory lectures, right? Here obviously I didn't have time, so use this only when you get diagonal matrix, then you can find it in seconds. Else you have to use the other rule, right? The Kalmar's test, basically the controllability matrix and the observability matrix. Okay, so I will write, because from diagonal matrix you can directly say what are my eigenvalues, right? Because it is only the diagonal elements. The diagonal elements itself are the eigenvalues. Gilbert's when A is a diagonal matrix, okay, A is a diagonal matrix basically. So yeah, when A is a diagonal matrix you use that. Okay, so now this is this one. So now let's go to our formal method, right? The method 2. Okay, so this one was the method 1. Method 1 basically, up until before this everything is in common, everything is in sync, right? And we'll go to method 2, basically the conventional method that we like generally do, right? Okay, so just generally do just method 2, which is the Kalman's test. Okay, what is the Kalman's test? Kalman's test is basically simply computation. Basically you have to check the controllability matrix and the observability matrix, right? So if my determinant of QC is not equals to 0, then that means my system is controllable, right? Control level. Okay, that means my system is controllable. Okay, so like what is QC? Like what is QC equals to? QC equals to simply B AB for second order, right? It is second order, so it will be AB. So I will find the determinant of QC. Okay, simply what is my B equals to? B is equals to 1 comma 1, right? 1 1. Okay, B is equals to 1 1, and I have to find AB also. Okay, so let me just copy this one. So what is AB? So I will just do it in rough, right? Very quickly. AB is minus 1 0 minus 1. Simply it will be 1 comma 1. It is simply this minus 1 and 0 and this 0 minus 1. So it is minus 1 minus 1, right? So directly from here I can see it is 0 itself, like the determinant is 0 itself, right? So it is minus 1 minus 1, right? And you find the determinant which is equal to 0. Hence from here I can directly say that this is not controllable. And what about my observability matrix, right? So QO is known as the observability matrix, and if determinant of QO is not equals to 0, okay, then I can say it is observable, right? Then I can say it is observable. Now if this is observable, like what is QO equals to? QO equals to simply this what do you say, C transpose A transpose C transpose. Like you might say, sir, where did this come from? So I have explained all this in my theory, so we are solving questions, so I don't have time. Okay, so now this is QO, right? Now what is C transpose? Basically C transpose is this, right? C is this, C is this, C transpose is 0 comma 1. Okay, so I have to find the determinant, right? Determinant of QO 0 1. Now what is A transpose times C transpose? So what is A transpose? A transpose is simply same itself, right? Minus 1 comma 0 minus 1 comma 0. And what is C transpose? C transpose is again, right, same thing itself. It is 0 comma 1, right? So what does this become? So this becomes minus 1 times 0 and 0 times 1. So this is 0, right? and this becomes 0 times 0 minus 1 times 1. This is minus 1. So I'm getting here 0 minus 1. So what is the determinant again? I can again see that my determinant is 0 itself. Determinant is 0 itself. So again from here I can say that it is unobservable. Sorry. So which option will be correct here? The option, right, this neither state controllable nor observable, option D will be correct here, right? So just be careful about this, right? That you can directly, like, it will take you like 1 minute max to get to this equations, right, and to write all this equation, and then from directly here, if it is in the diagonal form, you can directly say whether this is controllable or not, or state observable or not. If I have more than one Jordan block for repeated eigenvalues, then this won't be controllable and observable. If I have only one Jordan block for repeated eigenvalues, then I have to check further and use the condition, second condition, right? What is the second condition telling us? Second condition is telling us elements of B matrix corresponding to last row of Jordan block in E matrix should be non-zero. Okay. So basically, I don't have an example right now, but what I can say, like, this is one Jordan block, right, where like this is a 2 cross 2 Jordan block, and elements of last row, the last row is this one of the Jordan block. Okay, elements of last row is this one of the Jordan block. So then in the E matrix should be non-zero. Basically, this is the second row, right, and corresponding to the second row, if you go to the B matrix, right, and if it is non-zero, okay, it should be non-zero, at least one of the elements should be non-zero of this second row, right, of the B matrix, then this will be controllable. Okay, this will be controllable. Now what for the observability part? For the observability part, the first column corresponding to each Jordan block of C matrix should be non-zero. Now this is a Jordan block, 2 cross 2 Jordan block, and this is the first column, right, first column of the Jordan block, and you go down here, and this here, right, the C matrix resides. The first column of the like elements of the first column, any of the elements should be, like, any one of the elements should be at least non-zero. Okay, non-zero. Okay, so here, like, this is the, let's say this is the example, right, the second row and the like 2 cross 2 Jordan block I have, right. So the element corresponding to this and the element corresponding to this, right. Okay, let's say this is the example. Let me write this as 1, right. Let me write this as 1. Now what you will do, the element like, this is Jordan block, right, this is a 2 cross 2 Jordan block. Okay, I have repeated eigenvalues, but I have one above here, so I can continue. This is only, I have one Jordan block here. Now what do you see, the element corresponding to the last row of the Jordan block, element corresponding to the last row of the Jordan block of the B matrix should be non-zero. It is non-zero. Hence what you can say, it is controllable, right? It is controllable. Now what is the other case? Now element corresponding to the first column of the Jordan block, it should also be non-zero for observability. Hence I can say directly from here, this is not observable and this is controllable. What you do, your homework is you cross check, right, through the Kalman's test, basically the QC and QO, and you will find the same solution, right, that I give. That if you go along this direction, like if you go along this direction, this is non-zero, hence I can say this is controllable. But if I go along this direction, I can say this is not observable, right, because this is 0. Okay, I give you one example. So yeah, I will see you, like, if you want more questions, and like tell me what topics you want in questions, right, in control systems or any other subject, right. So I will try to provide that in core electrical also. If you want any question, any questions from any other topics, you can say me. I will provide you the with questions. So yeah, I hope to see you in the next video, and yeah, thank you for watching.